Hello, my name is Tomasz Idziaszek, and in this video I will talk about solutions to the Great Code-Off Challenge 2021 powered by Codility. In this challenge we are visiting a factory that produces cakes. Each cake should consist of exactly k layers. Each layer is of a different flavor, and the order of this flavor in the cake is very important. So we'll number these layers from 1 to k in the order they should appear in every cake. Cakes will be produced in forms. We have n forms arranged in a row, and initially they are empty, but there's a machine that will put certain layers into certain forms according to a given program. This program has m instructions, and the result of one instruction is putting a layer of certain flavor to all forms lying in a certain range. And the objective of this challenge is to write an efficient program that calculates how many well-prepared cakes there will be after performing m instructions. Let's take a closer look at the first sample test case. So in this test case we have 5 forms, and we will be producing cakes of 3 layers numbered 1, 2, 3. The producing machine has a program of 5 instructions, and they are encoded in arrays A, B, and C. The arrays A and B encode left and right endpoint of the range, and the array C encodes type of layer. The first operation is encoded by the first elements of these arrays. So it specifies that in the range from the first to the last form, the machine will put a layer of flavor 1. So we can put here these layers. In the second operation, the machine put layer 2 in the range from 1 to 2. So the image looks like this. The third operation concerns range from 5 to 4, and also the machine put a layer of type 2. For the fourth operation, the machine will put flavor 3 in all forms. So we can see that correct cakes are created in some of the forms, namely in forms 1, 2, 4, and 5. We have cakes of exactly 3 different layers, and they are in correct order 1, 2, and 3, looking from the bottom. Note that in form 3 we have incorrect cake because it consists only of 2 layers, but since the flavor 3 was put directly on flavor 1, so whatever the machine will do in subsequent operations will not fix this cake. Finally, in the last operation, the machine will put another flavor 3 only in form 4, and since it will be another layer 3 in this cake is also broken. So finally, after all operations, we have exactly 3 cakes that are well prepared. In the simplest solution to this problem, we just simulate all operations of the machine, and for each operation we go through the range of forms one by one and update the contents of this form. To simplify the implementation, you can observe that for each form we don't need to store all the subsequent layers. We only need to remember what is the flavor of the topmost layer in the cake. Or the cake is already in such a bad state, then nothing will fix it. If the cake is okay so far, the topmost value of 3 means that the cake consists of layers from 1 to 3, and the only correct extension for this cake is a layer of number greater by 1, so 4 in this cake. So if we get 4, we change the top number to 4, and if we get anything else, we say that this cake is broken. Broken cakes can be denoted, for instance, by putting -1 as their topmost number. Since we have m operations to perform, and in each operation we have to update up to n forms, and also update of the form is in constant time, then the total time complexity of this simulation is m times n. So let's implement this solution. So first I will create an array in which we'll keep the contents of each form. So the array will have length n, and I initialize each element by 0. So putting the layer number 1 will be correct extension of for all the forms. Next I will perform operations one by one. So I will just zip all the free arrays, and for each operation I will go for each form this operation specify. Here I number the forms from 0 rather than from 1, so I subtract 1 from the left endpoint. And now I perform the extension in the ith form. If the last layer in this form is one smaller and then the layer I want put in this form, I just change this layer to C, and else I know that this extension is incorrect one and this cake will be bad forever, so I put -1 here. Finally, I need to calculate the number of forms that have k as the topmost element, and I can use a standard Python method count to do this. Okay, so running test cases shows that this program successfully passes them, and when judged by Codility, it will get full marks for correctness. But since both n and m can be numbers as big as 10 to the power 5, our program will try to perform 10 to the power of 10 operations and won't get point for performance. In order to get a more efficient solution, we must perform the operation faster. Since each operation is restricted to a certain range or a segment, we can use a data structure called a segment tree to store information about the forms. Such a data structure is a full binary tree in which every node represents a certain range of forms. Each leaf in a tree, so a node in the bottom layer, represents a single form, and each inner node represents a range obtained by merging ranges from its left and right children. In particular, the root of the tree represents the whole row of forms. Note that since a segment tree is a full binary tree, the number of its leaves is a power of 2. If n is not a power of 2, we can keep adding empty forms to the end of the row until it becomes 1. The length of the row will not increase more than twice. If we number the nodes layer by layer, starting from 1, we can keep them efficiently in a table of length 2n without any pointers, because the left and right children of a node number v will be 2v and 2v plus 1 respectively. Let's analyze another example to see how the operations are performed on the tree, and also what information should be stored in the nodes. The first operation puts a layer of type 1 to the range of the forms from 0 to 4. We would like to put information in some nodes of the tree that covers the range from 0 to 4. Of course, we could put information in the leaves of the tree which covers this range, but more efficiently would be to put this information in node 2, which covers the whole range from 0 to 3, and node 12, which covers the range 4. This way, we put information only in 2 nodes rather than 5. Using the same approach, the information about the second operation that puts layers in range from 6 to 7 can be stored only in node 7. And the information about the third operation that concerns the whole row of forms can be stored in the root of the tree. In order to read from the tree what layers are present in a certain form, we start from a corresponding leaf and go through the chain of parents up to the root of the tree, and we concatenate the information in these nodes. The root of node v has number v divided by 2. So if we want to be able to retrieve the information about the order of the layers in a certain form, we must keep the invariant that the layers are in correct order when we are going from the leaf to the root. Because of that, we cannot store the information about the third operation, which involves range from 4 to 7, in node 3, which precisely cover this range, because then the order for the form 4 would be 1, 3, 2 rather than 1, 2, 3. So if we want to make sure that layer 3 is the last layer on this path, we must somehow remove the information from the root. We will do this by propagating the information from the root to its children. So we will add layer 2 to nodes 2 and 3 and remove it from the root. And now it's safe to add information about the fourth operation to the node number 3. The method we used here, in which we move information from a certain node to its children, is called lazy propagation. Lazy because we try to avoid doing this work as long as possible. Let's look once more how it works, now in operation 5, in which we put one layer in the form number 2. In order to do this, we must propagate information from node 2 to its children, then from node 5 to its children, and finally we can add information about layer 3 to node 10. In each node we store information about some layers that were put in the range corresponding to this node, and if this partial information is correct, then the numbers of these layers must be consecutive. Therefore, we can store this information compactly as a pair, the type of the lowest layer, and the total number of layers. So the information in node 3 can be stored as a pair 2, 2. Also, when performing lazy propagation, we must be able to combine information in the children node with the information which comes from its parent. So, for example, if we propagate the information from node 3, the information in node 7 will be written as a pair 1, 3. The information in an empty node can be stored conveniently as a pair with the second coordinate equal to 0. Finally, we need to cover the case in which a partial solution is broken. For example, after performing the 6th operation, we would get the order of layers 1 to 1, and we can represent such a broken solution with a pair with -1 on the second coordinate. So now, when we saw how to perform the operations on the segment tree, the crucial question remains: what is the time complexity of this approach? Work which we do in every visited node, due to lazy propagation and combining information, takes constant time per node. Therefore, time complexity depends on the number of visited nodes during the operation. And it can be shown that during an operation for a certain range, the set of visited nodes is limited to the leaves in the endpoints of this range, the paths from these leaves to the root, and children of the nodes on these paths. Since the height or number of layers in the full binary tree with n leaves is equal to logarithm of n, therefore the lengths of the paths from the leaves to the root are also logarithmic, and the total number of visited nodes will be 4 times the height of the tree. Therefore, the time complexity of a single operation is logarithm of n. Therefore, the total time complexity of this solution will be O of n, because we need to initialize the data structure for the tree of size n, plus m times log n, because we perform m operations, each in time logarithm of n. Of course, at the end, we must produce an answer, so the number of forms with well-produced cakes. This can be done in MlogN time by querying forms independently, that is, by traversing all paths from leaves to the root, or in linear time by iterating through the nodes from top to bottom and propagating all information to the leaves. After that, we only need to calculate the number of leaves in which the information is a pair 1k. So finally, let's implement the solution with the segment tree. First, I will calculate the number of leaves in my segment tree. So I will find the smallest power of 2, which is not greater than n. And I will store the information in one array of size base times 2, because I need this number of leaves and also additional this number of entries for internal nodes. And in each node, the initial information will be empty, so we will represent it as a pair in which the second coordinate is equal to 0. All right, and the big picture for the program is as follows. First, I will perform all operations, and for every operation, I will perform something on a tree. So I will add this information, and after that I will perform the final lazy propagation to all leaves, and I will count the correct leaves. For operations on the tree, I will use recursive approach from top to bottom. So I will start at the root and move to nodes in lower layers if necessary. So that's why, apart from the arguments a, b, c that encodes the operation, I also need information in which node I'm currently in, and also which range this node represents. So I will start here in the root, so node number 0, and this node represents the full range from 0 to base -1. And now I consider 3 cases that depends on the relation between range AB and range XL XR. If these ranges are disjoint, so the range AB does not touch node V at all, then I will just return. In the second case, if the range of the node is fully contained in the range AB, I can store the information about layer C into node V. I will do this by combining any information in which is already stored in node V with additional information about one layer C. So this information is encoded as a pair C, because this is the first layer, and 1 because we have only one layer. We'll get back to the function combined later. Finally, the last case is when our range AB partially covers the range of node Z, and then we need to make recursion calls to both children of node V. But before that, we need to make a lazy propagation. So we need to combine information in children of node V, and these children are numbered 2 times V and 2 times V plus 1. So we combine their information with information which was located in its parent. And after this propagation, we remove the information in the parent. Finally, we make a recursive descent to both the children. So we perform 3add on vertex 2v. And now we need to calculate the range for this vertex. So the left endpoint stays the same, but the right endpoint will be the middle point between XL and XR. And for the second child, we do similar, but the right point stays the same. Okay, now it's the time to show the function combine. So we get 2 pairs that represent information in the nodes. So these pairs can be unpacked as a first layer and the number of layers or size. And if the size of the first or the second pair is -1, then we know that the result is a broken partial solution. So the combination of these partial solutions will also be broken. Else, if one of these solutions is empty, we just return the second one. Finally, we have a non-trivial combination. So we look at the number which is expected as the next number after the first partial solution. And if this number is equal to the first number and the second partial solution, then we extend this. So the partial solution starts from the lowest layer in the first solution, and the length of this solution is the sum of the lengths. If it's not the case, then we know that the answer will be a broken partial solution. The last thing to implement is the function treeCount, and this function will also be recursive, and we will start from the root, and if the vertex or the node we are considering is a leaf, so its number is at least base, we look at the information in this node and return 1 if and only if this information shows a correct cake in the leaf. For the inner nodes, we first make lazy propagation, and then recursively go to the children and sum the answers from these children. All right, let's look at the tests. Okay, the solution works correctly here, and it will get a full score when judged by Codility. This solution using a segment tree data structure is not the only efficient solution for the challenge. There's an alternate solution that uses a so-called sweep line method. In fact, this alternate solution can be even implemented in linear time n+m. I encourage all viewers to invent and implement such a solution.